So today we're going to talk about downstream purification, TFF applications, and specifically we're going to talk about TMP, transmembrane pressure control, and UFDF, ultrafiltration, diafiltration, TFF installations. Tangential flow filtration, TFF, is a pressure-driven membrane filtration separation process that's commonly used for downstream purification and concentration of biomolecules in ultrafiltration and diafiltration. It is also sometimes used upstream in perfused bioreactors and also, not as often, but in clarification, although that is becoming more frequent as TFF systems evolve. So how does a TFF system work? As shown in the illustration, bioprocess fluids are recirculated via a pump and tangentially flow across, in the illustration, a tubular porous membrane. And the tangentially, that's where the T in TFF comes from, of course. It's worthy to note that there are also non-tubular designs, such as flat or plate cassette type membranes that are used as well. But all of them are TFF, and the flow, again, flows tangentially across the surface of the membrane. TFF membranes are sometimes called cross-flow filters or cross-flow membranes, but they all reflect the fact that the flow is flowing tangentially across the surface of the membrane. They all work the same. Since the recirculating system is pressurized by a pump, pressure forces the smaller molecules in the recirculating fluid to pass through the membrane pores. And you can see that in the illustration. The dotted line here represents the pores in the membrane. You can see that all of the orange and red smaller molecules are filtering through, while the blue particles, the larger particles, are unable to pass through. And that's basically how it works. But you need pressure for this to work right. Since the system is pressurized by a pump, pressure forces the smaller molecules to pass through the membrane pores. They permeate the membrane, hence the term permeate. You can see that on the far right of the illustration. Larger molecules, the blue ones, can't pass through, and they are retained as retentate, as we've got that marked on the illustration as well. So the cross-flow part of tangential flow, and the reason that this method was created, is so that the constant feed flow washes anything that might get stuck in the pores through the system. Anything too big to permeate the membrane, the flow will wash it off the surface of the membrane and it'll recirculate. That's what we're trying to do there. So the key point here, we have to maintain a pressure difference between the circulating fluid and the other side of the membrane, as that is what drives the what's called the flux rate. Flux rate is the permeate flow rate per unit area of the membrane. If you just think of permeate flow rate, that's good enough. So that pressure difference across the membrane is called the transmembrane pressure, or TMP. And in the illustration, you'll see I've got P1, that's the retentate pressure on the retentate line, and P2 is the pressure on the other side of the membrane. So transmembrane pressure really drives that migration of those smaller molecules across that membrane, and that's important to remember. So take a look at the graph here. TMP, along with the feed flow, determines that permeate flux rate. And again, that's the flow rate per unit area of filtered media. TMP really drives the process. As TMP increases, as you can see on this graph, the permeate flux initially rises, but eventually at the top of the graph, and you can see that right here, it plateaus. As excessive TMP, if my TMP is too high, it leads to membrane fouling. So what's happening if my TMP is too high is that molecules, the bigger molecules, are getting squished into the side of the membrane, into the pores, and it's clogging it up, which is why the flow is dropping off. And you can see that on the graph where it plateaus. So taking a look at a little bit more of the strategy as to how TFF is going to work to separate a particular biomolecule that we're after. That strategy of feed flow and permeate flux rate is determined during process development and scale up. The idea is always to balance the filtration efficiency and membrane longevity. Excessive TMP accelerates the fouling, or it's called gelling sometimes, and reduces long-term filter performance. However, if TMP is too low, it lengthens the filtration batch times and increases recirculation exposure in batch processes. And that's not good because that can cause molecular degradation or dissociation of molecules. For one, the longer I run that batch, the probability of degradation or dissociation gets faster. And again, my batch is taking too long to process. So in summary, controlling the optimal TMP set point is critical for efficiency and biomolecular quality. Holding TMP firm improves filtration efficiency as controlling TMP affects the permeate flux rate. Holding TMP steady improves and affects biomolecule quality. Also, optimal TMP can increase the membrane's lifespan, reducing the probability of the membrane getting gelled over. Remember, if I have my TMP too high, it's going to squish molecules into the surface of that membrane, and it's going to gel up and decrease the efficiency of the membrane. One last point on this, and it's related to the quality point above, increased TMP or TMP fluctuations can expose biomolecules to shear forces, ultimately lessening the amount of useful biomolecules that we produce. And by the way, we'll see that later in an experiment that was conducted that I'm going to share with you in a couple of minutes. So how do we control TMP and what types of valves are used? It depends upon the type of system you are working with. In traditional multi-use stainless bioprocessing systems, a conventional sanitary rising stem pressure control valve have typically been used. And why? These control valves have the better turndown, a maximum of about 40-to-1 turndown. And they are better than the alternative valve that you might be able to use, which is a sanitary back pressure regulator. And traditional sanitary back pressure regulators have lesser turndowns of about 25-to-1 at best. So, and just to remind everyone, turndown refers to the minimum and maximum flow rate that a valve can actually control flow at. That's what turndown is. So the higher the turndown, the better. The higher the flow range the valve can handle. And also as process conditions change, like they do in TFF, when I'm concentrating something, the density and viscosity change, the higher the turndown, the more likely the valve is going to be able to control across the entire range. So how many valves are needed and where are they placed in this system? That again depends upon the system design. If the permeate goes into a holding vessel, like it's shown here in this illustration, and that holding vessel has a sterile vent filter, as I'm showing here, the transmembrane pressure will be P1, the retentate pressure, minus 0, because if my permeate is sterile vent, if it's vented, the permeate pressure is going to be 0. So my TMP is going to be basically what my retentate pressure is. If the permeate does not go into a vented vessel, that's a little bit different story. If instead the permeate is immediately pumped downstream for additional processing, then the P2 pressure will vary as that pump pressure is going to vary. The suction line pump pressure is going to vary. It's not going to be at a constant figure. So in that case, I need a second valve on the permeate line, but only in that case. I think you'll find, at least in my experience, most systems have it where the permeate is vented to atmosphere. So typically you only need one valve for this application. So I mentioned earlier, I talk about an advance in TMP control technology, and that's what I'm going to do now. So in multi-use stainless systems, the Equilibar Model FDO, it's an air-loaded back pressure regulator. It demonstrates a significant advance in pressure control for this application. That's because the FDO has a 10,000-to-1 flow turndown range and exceptional stability. And to see that, take a look at the test chart that's on the left side of this slide. And you'll see there that we are controlling inlet pressure and recording inlet pressure at various flows from 0.001 gallons a minute up to 10 gallons a minute. And you can see the stability across that flow range is insane. It is 10,000 to 1 turndown, which is fantastic for this application, again, because the process conditions on TFF change as fluids are concentrated and the flow rate changes as well. So pretty cool thing. I'm going to show you how the back pressure regulator, the FDO pressure regulator, works. And how does it work? It works very simply. Again, it's an air-loaded valve. So air or gas pressure is added to the top of the valve. You can see that over here, right into this port right here. And it's added by either a simple pressure reducing valve or, if automated, using an I to P or E to P, depending upon where you live in the world, what it's called. That pressure is loaded in there is the valve's inlet pressure set point. So that air load pushes a PTFE or elastomer diaphragm, which you can see there where I've shown diaphragm. That pressure pushes the diaphragm down over an orifice field that's machined into the top of the body. So if I've got 5 psi, a 0.3 bar air load pushing into the top, and I have no pressure under that diaphragm, what's the diaphragm going to do? It's going to lay flat over that orifice field. So when process fluid enters the valve, and you can see the orange arrows below right here. So the process fluid enters here, is distributed around the perimeter of the valve. You can see this channel right here. And it goes around that channel and migrates over the top of the orifice plate, and then it goes through the orifice field holes and out the outlet. Really simple process as to how that works. So if the process pressure under the diaphragm equals and begins to barely exceed the pressure of the air load, what will happen? The diaphragm will begin to lift off the orifice, will lift off 1 or 2 of the orifices, and your flow will exit through the orifices and out the outlet. As additional volume pump ramps up, and I've got additional flow coming into that inlet on that valve, what will happen is the additional volume will increase additional pressure under the diaphragm, which will, if the flow is great enough, lift it completely off all the orifices, and I'll be at max flow. This is how this works. So the pilot pressure is my set point, and the inlet pressure, as we saw in the previous graph, will remain rock steady regardless of what that flow is, over a 10,000 to 1 flow range, which is totally insane. It's amazing tech. And I'm so happy that I've had the opportunity to work with this innovative company. It's a rare thing in a career to get to work for a company that makes game-changing tech that works better, and that's exactly what this technology does. On the single-use side, it's exactly the same tech. It works exactly the same idea. I'll show you how the cutaway of the SDO, the single-use valve, in a moment. The only difference is this valve will hold inlet pressure rock steady over 1,000 to 1. Not quite the same as 10,000 to 1, but it's still more turndown range than any biopharm application that you will ever come across. The SDO, the single-use valve, this is our newest tech, and it was released about 2 years ago. And as you can see in the illustration there from a company called Tesalon, that's one of the OEMs that's adopted this for their single-use TFF skids for retentate pressure control. So exciting stuff. Here's a cutaway of the SDO. So the SDO is a single high-density polyethylene body, that's the white, that's been welded to a very thin high-density polyethylene diaphragm that you can see there. It's assembled in one piece. It fits into the lower part of the stainless part, which is called the cradle, and it sits in that cradle, and then you put the top, which is called the reference cap. You set that down on top, and then you tighten the thumb screws. That's how this gets assembled. So during assembly and installation, this body assembly, this SDO valve, would be pre-assembled to a single-use throwaway tubing connected to the hose barbs with Oetiker clamps or however you want to clamp it. And then that assembly, of course, would be laid down into the cradle and the reference cap tightened after that. So that's how that works. And by the way, the valve body and diaphragm are welded, assembled, and tested in an ISO 7 clean room from components that meet all the applicable USP and ISO standards. And if anybody's interested, we can send you that documentation. We have a document that covers that, as most single-use folks do. So that's how that valve works. So I mentioned earlier that we've done testing. Equilibar's done testing for years and years, and several years of testing on TFF. And I'm going to share one experiment that we did in-house with you. And this was to evaluate the TMP performance of the SDO and comparing its performance versus industry standard pinch valves. The only regulator that's been around in the industry prior to the SDO single-use regulator has been tubing pinch valves. The orange squiggly lines are the pressure maintenance of the pinch valve, and the SDO is the recorded pressure. That the blue line is the SDO recorded pressure. So really stable pressure. The pinch valve really struggling to maintain that pressure. And that's on the left, that's TMP versus time. For permeate flow versus time, we also recorded that with a 10 PSI set point. Again, the permeate flow very stable relative to the pinch valves flow measurements that were taken. So just a great valve, great technology. Not surprising to us, we knew this. So why is there this difference in control? The root cause of the instability lies in the nonlinear pressure response of pinch valve mechanisms and the variable resistance of physically trying to pinch. Very difficult for precise, repeatable TMP regulation. Pinch valves operate also in kind of more of a discrete manner than does our valve, which is really a continuous control mechanism. And also, when you pinch tubing, if you've ever tried this more than 50% with a pinch valve, trying to make small adjustments beyond that cause large TMP changes because of the reasons I explained above. And it's difficult to bring a pinch valve, if it's automated with an actuator and a positioner, back under control when the system fluctuates a lot. The Equilibar SDO maintained a precise and stable TMP and flow throughout the experiment. And unlike the pinch valve, the operation of the SDO allows it to respond instantly to system changes due to its simple air load design. The air acts directly on the control mechanism. The flow control mechanism is the diaphragm, and the air is pushing down directly on that. So just incredibly simple. There is no linkage. It's just the diaphragm against the orifices to control flow. So it's very immediate, and it's incredibly accurate as well. So the large flow turndown ratio and direct pneumatic control ensure continuous and proportional pressure adjustments if you automate this valve. And by the way, the same comparison is true for control in a stainless steel system using the stainless steel FDO. As with the SDO, the air acts directly and immediately on the FDO diaphragm, which is the control mechanism. And we can contrast that with a traditional sanitary control valve, where I've got air going into a positioner, into an actuator on top of the valve. The actuator pushes down on usually at minimum of 2 valve stem sections, which then pushes or pulls a plug on the end of that stem out of a conical orifice. So it's just, again, you've got hysteresis that happens on traditional sanitary control valves that you don't have, and a lot of tolerance stack up that just messes with the accuracy relative to using an FDO. And by the way, both the FDO and the SDO, this is a subject for a different time, but can be used for incredibly precise flow control. I'm not going to say more on that other than we'll do a webinar at some point in the future specifically on that subject. So we did a second experiment. And in this experiment, Ryan Hefner, who was our single-use technology officer at Equilibar, he hired a company in Salem, New York, BioX, to do this test. And the test was commissioned to evaluate the performance of an SDO versus a pinch valve on a UF-DF system for concentration of IgG, immunoglobulin G, using different pumps, a biofarm centrifugal pump, a peristaltic pump, and a quaternary diaphragm pump. In other words, this was a real-world process concentration application using all the pump configurations that the industry uses. The setup is described in a little bit more detail in the graphics. And I'm going to go through this. Guys, all of you that are attending will get a copy of this webinar so you can look at this at your leisure later. So one of the results of this test was not surprising to us. The SDO outperformed the pinch valve regardless of the pump employed because of its ability to hold stable TMP regardless of feed flow conditions. So what ended up happening is that our spec target concentration occurred with less cycle time, regardless of the pump. It outperformed the pinch valves by a range of 14 to 23 minutes, depending upon the pump type. So we get through batch to batch concentration a lot earlier than you would with a pinch valve. And related to this, but not measured, but still known, is that because the SDO or FDO hold TMP rock steady, the probability of membrane fouling, gelling, is definitely reduced. So from a time standpoint, over the average of multiple batch times, again, you're going to save a lot of time just based on that fact alone, because the probability of gelling goes way down. More surprising to us were the deviations from baseline concentration. You can see that in the chart that's at top. Here it was discovered that the SDO valve reduced IgG loss through molecular dissociation by approximately 1%. And basically what that means is the biomolecules weren't destroyed or damaged, so less were lost. In other words, the SDO treats molecules in this system more gently. 1% seems meaningless until you put it in concept. A 1% loss of a small scale MAB batch would translate to about a $10,000 revenue loss, to put that in more meaningful terms. And that was impressive to us. It was impressive to the folks at BioX that tested this. So guys and ladies, that's all I have for you today. Thank you very much for attending. We appreciate it.